Section 7.3, Logarithmic Functions as Inverses. Today we're going to write and evaluate logarithmic expressions, and we'll probably go through the graphing logarithmic functions tomorrow, so it's a 2-day lesson. Logarithm, base b of a positive number x satisfies the following definition. For any numbers greater than 0 where the b is the base of the log, and it cannot be 1, you can rewrite logarithmic equations to exponentials and back. So log base b of x equals y, that's the log equation. You're going to rewrite it as an exponential. So what happens is the base of the log gets swung over and it becomes the base of the log. So this expression gets rewritten like that one. So b to the y equals x. It's read log base b of x on the left side. The logarithm y is the exponent to which b must be raised to get x. So let's look at a couple examples. What is the logarithmic form of each equation? So these, we're trying to write the log, so we're going to go backwards. The base of the exponent becomes the base of the log, so we're going to swing that base back over. Log base 10 of 100 equals 2. That's all you do. So the base of the number becomes the base of the log. So log base 3 of 81 equals 4. Let's pause the video now and practice got it number ones, A, B, and C. The base of the number becomes the base of the log. So log base 6 of 36 equals 2. Part B, 8/27 equals 2/3 cubed. The base of the number becomes the base of the log. So log 2/3 of 8/27 equals 3. It looks really goofy, but that's what it is. You can have fractions as long as they're bigger than 0 and not equal to 1 for the base. One more example from got it number 1. The base of the number becomes the base of the log. So log base 3 of 1 equals 0. Problem number 2. What is the value of log base 8 of 32? Well, we don't know what the value is, so let's set it equal to x. Log base 8, 32 equals x. We don't know how to solve log equations yet, so we need to rewrite as an exponential. The base of the log becomes the base of the exponent. So 32 equals 8 raised to the x power. Once you swing that base over, the word log is gone. You've rewritten. Now, we don't know how to solve this either because we'd have to take the xth root of something and we don't know what that is. So what we're going to do is we're going to rewrite each number so the bases are the same. So 32 I can write as 2 to the 5th power. 8 I can write as 2 to the 3rd power. And what happens is I can multiply these exponents together. So I have 2 to the 5th equals 2 to the 3x. Now since the bases are the same, the exponents must also be the same. And then it becomes just a basic little equation that you solve on its own. So x is equal to 5 over 3. I would not write that as a mixed number just because it looks goofy and it's harder to tell what's what if you don't keep it as an improper fraction. Let's pause and try these got it questions. What is the value of each log? Part A, log base 5 of 125, set it equal to x first. And remember the base of the log becomes the base of the number. So it's 125 equals 5 raised to the x power. I know that 5 is a prime number, so the right side is simplified. I can write 125 as 5 to the 3rd power. And now since the bases are the same, the numbers, exponents must be the same as well. Let's try B. Log base 4 of 32, set it equal to x. The base of the log becomes the base of the exponent. So 32 equals 4 to the x. 4 is not a prime number, so I'm going to take that down to a 2. 32 I can take down to a 2 as well, 2 to the 5th. I can multiply my exponents on the right. And now since the bases are the same, the exponents must be the same. I don't know what's going on with my pen. So 5 equals 2x, and then I divide by 2, and I get x equals 5 over 2. I'm not sure what's going on with my pen or my recording here. Log base 64 of 132, set it equal to x. So this becomes the base of the log, becomes the base of the exponent. So it's 1 over 32 is equal to 64 to the x. Now this is the hardest one. First of all, 32 is on the bottom, so I'm going to bring it up. And when I do that, it gets a negative exponent. You want to always bring these down as low as you can. So I'm going to rewrite 32 as 2 to the 5th power. I'm going to keep that negative 1 there for now. 64 becomes 2 to the 6th power. So I'm going to multiply each of those. 2 to the negative 5 equals 2 to the 6x. And then since my bases are the same, my exponents are the same as well. Negative 5 equals 6x. X would be negative 5 over 6. A common logarithm is a logarithm with base 10. Sometimes they write it, sometimes they don't. So when you look at the next expression, you can write common log base 10 of x, which is the same as log x. So when there's no number right there, it's an automatic 10. You don't need to write it, but you can if you want to. The Richter scale is an example of the logarithm of a quantity instead of the quantity itself. It gives the log measurements of earthquake magnitude. Check out the number line at the top of page 433. Our next problem, problem number 3. In December of 2004, an earthquake with magnitude 9.3 on the Richter scale hit off the northwest coast of Sumatra. The diagram on page 453 shows the magnitude of an earthquake that hit Sumatra in March of 2005. The formula, log the intensity 1 over intensity 2 equals m1 minus m2. So what those letters stand for is I is the intensity level of the first one and the second one. M is the magnitude of the first one and the second one. How many times more intense was the December earthquake than the March earthquake? So we start with our formula. And it equals m1 minus m2. Okay, so looking at the table, m1 is 9.3, m2 was 8.7. So I'm going to subtract those, and I get log I1 over I2 equals 0.6. Now remember, when there's no base, it's an automatic 10, and what we're going to do is rewrite it. So we're going to do the same thing that we've been practicing. We're going to swing that base over, and it becomes this. I1 over I2 equals 10 to the 0.6 power. Well, if you simplify 10 to the 0.6 power, you get 3.98, which is about 4 times bigger. or stronger. Let's pause and practice got it number 3. In 1995, an earthquake in Mexico registered 8.0 on the Richter scale. In 2001, an earthquake of magnitude 6.8 shook Washington state. How many times more intense was the 95 earthquake than the 2001 earthquake? So we'll start out with the same formula on this one. Log I1 over I2. We're going to take the magnitude of the first one minus the magnitude of the second one, and we get 1.2. Remember that there's a 10 right here that gets swung over when we rewrite, and it becomes I1 over I2 equals 10 to the 1.2. We do a little simplifying, and we get about 15.8, which is 16 times stronger. The logarithmic function is the inverse of an exponential function. See the graph on page 454, which shows the graph of the log function and its inverse. So take a look at that. What we're going to do is we're going to graph y equals log base 3 of x. We're going to figure out what the domain and range are and identify the y-intercept and the asymptote. I was going to put graph paper on here, but I forgot, so I'll just hand draw this one. Make sure you guys use graph paper, please. So this is only going to be in the first quadrant generally, so we don't really have to worry about doing the other 3. What we're looking at is how do we know what to graph, because we don't know how to do log base 3 of x. So what we need to know is y equals log base 3 of x is the inverse of y equals 3 to the x. So when you're looking at it, if you just kind of ignore the word log, the inverse comes right off of that. What we're going to do is we're going to pick numbers to go into the inverse instead of the log equation. All right, so we need numbers that are going to be decent numbers to graph. So I'm going to start with -3, -2, -1, just because we haven't seen one of these yet, and then 0, 1, 2, and 3. I'm going to plug it in, so 3 to the -3 is 0.04. That's not very easy to graph, so we're going to keep on going. 3 to the -2 is like 1/9, which is about 0.1. That's okay to graph. We're going to keep going. 3 to the -1 is like 1/3 or 0.3, and 1 decimal place on these would be okay. Then we get to 0. 3 to the 0 power is 1, because anything to the 0 is 1. 3 to the first is 3. 3 squared is 9. And 3 cubed is 27. We're going to run out of room before we get to that one. Remember also that when you are graphing, there's an invisible diagonal line. Sorry about that. At 0, 0, 1, 1, 2, 2, 3, 3, and so on. That's our y equals x. So I'm going to do this first one in purple. This surface is kind of going crazy here. -3 is 0.04. Very, very small. -2 is 0.1, a little bit higher up. -1 is 0.3. All right, 0, 1, 1, 3, 2, 9. So it kind of looks like this. And remember, it is a curve, and it doesn't cross over that x-axis. So what we're going to do, since this is the inverse of our normal equation, we're going to plot the points of the inverse. Sorry once again. Okay, so we're going to graph 0.04, negative 3. So we're flipping these, okay? So my inverse, this one, is going to be in pink. So remember to reverse your ordered pairs. 0.1 would be at negative 2. 0.3 is at negative 1. 1 is at 0. 3 is at 1. 9 is at 2. So this one looks like this. And if you flip them over the green dotted line, they should look the same. Now, we are looking at the pink one only. So this is the one that we're kind of concentrating on. So we graphed the inverse, and then we had to flip the ordered pairs back over to get the actual equation that we were looking at. So my domain this time looks like it's only going to be numbers bigger than 0. So x is greater than 0. My range this time is it keeps on going down, so it hits all the negative numbers. It keeps on going to the right, so it hits all the positive numbers. So that looks like all real numbers to me. Then we have the y-intercept. So is there anywhere that crosses the y-axis? And that is a no, so there's none. It gets super, super close to it, but it doesn't cross over. And then the asymptote line is the line that it gets super, super close to. So when we're looking at that, that would be this vertical line. I'll make it orange. Right here. So the vertical line, remember, is an x equals line because it goes through the x-axis. So my asymptote is at x equals 0. Let's look at another one of those. Why don't you pause it and try? Got it, number 4. So again, I'm going to put some graph paper. For this one, I'll draw it in again. I'll go like that. So the inverse of this one would be y equals 4 raised to the x. So that's the one that I'm going to pick ordered pairs for. And I'm not going to graph my inverse. I'm just going to graph the reverse of it. So I'm going to pick numbers to plug in. So I'm going to go -2, -1, 0, 1, and 2. If I plug a -2 into 4 to the x, I get 1 over 16, which is about 0.1. If I plug a -1, I get 4 to the -1, which is 1/4, or about 0.3. I think my battery is going dead now. Perfect. I'm going to pause for a second. So, sorry about that. I've had all sorts of things happening. This is the 4th time I've tried this video. I had to restart. It kept going back to the beginning, and then it kept going pages over top of mine. So hopefully we can get through it this time. So as I was saying, I'm plugging numbers into 4 to the x, and that, remember, is the inverse of what we wanted it to be. 4 to the 0 is 1. 4 to the first power is 4. 4 to the second power is 16. But remember, that's the inverse. So what I'm going to do is I'm going to actually graph the reverse of these. Okay, so I'm going to be graphing these. This one, 0.1, -2, 0.3, -1, 1, 0, 4, 1, and 16, 2. So those are the ones that I'm actually going to graph. So I'm only graphing the actual equation this time, not the inverse, so that I flip it over, because all we do is switch the ordered pairs anyway. All right, so point 1 is at -2. So super close to that y-axis. Point 3 is at -1. 1 is at 0. 4 is at 1. And 16 is at 2. So I think I only got to 12. So I'm going to just draw it in like this. Okay, it'll look kind of like that. Okay, so my domain looks like all numbers bigger than 0. My range, it looks like it hits all the negative numbers as it goes down the y-axis and all the positive numbers, so I'm going to go all real for the range. The y-intercept, there is none because it does not cross the y-axis. And the asymptote line, remember, is the line that it gets super close to but doesn't go across, and that line is the vertical line, x equals 0. See the concept summary on page 455. So rather than graphing all of these, we're going to describe some of those equations as well. So how does the graph of y equals log base 4 of x minus 3 plus 4 compare to the graph of the parent function? So when you're looking at it, the things that have changed would be these two parts. If you can describe what those things do according to what we already know, that's all you're going to have to do this time. So the plus 4 makes it go up 4. The x minus 3, remember if you solve this one, you get x equals 3. So even though it says minus, this would mean 3 units to the right. So I'm describing this as 3 units to the right and up 4. When you're looking at this one, if you actually graphed it, here's what's going to happen to the domain, the range, the y-intercept, and the asymptote line. So the domain, since we are moving it right or left, that does affect the x-axis values. So the right 3 then, instead of being an x greater than 0, it's going to be an x greater than 3. The range values stay the same because that was all real numbers before. It doesn't matter if you move it up or down, the range is going to stay all real numbers. There wasn't a y-intercept before, so when you move it 3 units to the right, there still is not a y-intercept. Now this one might change if you move it to the left, however. You'd have to pay attention to how many units left you'd go. And the asymptote line also moved to the right, so that's going to be at x equals 3. So just kind of pay attention to those. You could put them on a graph paper, but I just kind of wanted to describe what the changes were. So this one is affected by the move right, and so is the other at the bottom. So right 3 affects both the domain and the asymptote line. Here's a got it question. You can pause and try these next two. How does the graph of each function compare to the graph of the parent function? Once again, this one is actually the same as what we just did. So this one is up 4. This part right here would be right 3. Now I just went through the domain and range on this one, so I'm not going to do that one again. Y equals 5 times the log base 2 of x. With this one, there isn't an up down, there isn't a right left. The only number that's ahead of this is this 5, and that means it's going to stretch 5 units. Now, a stretch of 5 actually affects the range only, and the range was all real numbers before. So all of these domain, range, asymptote, and y-intercept are all the same as before.